Categorical cross-entropy loss. In the last few lectures, we were looking into different loss functions that are used in machine learning. Initially, we were looking on to different regression loss functions. After that, we slowly moved on to classification loss functions. In classification loss functions, what did we already learn? Already, we learned about binary classification loss functions. And now we are slowly stepping on to multi-class classification. In multi-class classification, the first one we are going to learn is categorical cross-entropy loss. We have already learned about another cross-entropy, that is binary cross-entropy loss. Binary cross-entropy was used in binary classification, and this one is almost the same logic, but we are going to extend it to multi-class classification, right? Let us see what is categorical cross-entropy. You have to understand, when I say multi-class, that means each input belongs to exactly one class out of k possible classes. It is not like same input can belong to multiple classes. It is that there will be multiple classes out of which there is only one class to which your particular input belongs to. Okay, we'll say there are k different classes. First, we'll see how this is related to binary cross-entropy. Then we'll understand categorical cross-entropy in detail. We'll see complete derivation of this, and then the whole idea will be clear for you. Okay, let us start with this. First, I'll make the terminology clear for you. First thing you have to understand here is number of classes k. Let us start with this only. This is the number of classes. This is something that we are newly introducing. In binary cross-entropy, we just had two classes, so we didn't require this particular k. Here we are having number of classes as k. Next thing is, you will have something called as true labels. True label can be something like 1, 2, 3 up to k. So any of these are true labels. What does true label mean? Given an input x, okay, let me mention that as well. X is the input. Given any input x, which class does it actually belong to? That is your true label. Now, you are not going to express true label simply as a number like this. Instead, it will be expressed as a one-hot vector. This one-hot vector will look like this. A vector y equal to, it will have y1, y2 up to yk. This is a one-hot vector. Why is it called a one-hot vector? What is the speciality? A one-hot vector will look something like this. Let us say 0, 0, 0, 1 or maybe 0, 1, 0, 0. The reason it is called as one-hot is that one particular entry will only have a value. Value in the sense a positive value. All others will be zeros. That indicates which particular class it belongs to. Let us say there are three classes, 1, 2, 3 and 4. Then wherever you put 1 in this vector, that is the class it belongs to. So let us say this is your one-hot vector. This means this particular input, let us say you have some input x, and then corresponding to this x, y, that is your one-hot vector is this. That means this input belongs to class 4, because in 4 you have a 1, all others you have 0. Let us say instead of this it is like this, 0, 1, 0, 0. What does this mean? The input belongs to class 2. This is what you call as one-hot vector. Okay, only one particular value will be equal to 1. So you can say out of these, one particular class yk will have value 1, and all others will have value, all other yi's will have value 0. This is when you call it as one hot vector. Okay, so at this point it is clear what is the input. How will your output be represented? Output means the true label, not the output of model. Here we are representing the true label. If x is the input, what is the true label that it belongs to? Okay, automatically the next question is, how will the output of model be represented? That is y cap. What is y cap? Y cap will also be a vector, But this is the raw outputs. That is, you will have something like this. You will have y1 cap, y2 cap, similarly up to yk cap. This is the output of the model. So it is like this. If you have a model here, you are giving an input x to the model. Your model will be outputting y cap. This y cap will not be a one-hot vector. It is not a one-hot vector. It is also not probabilities. Instead, it will just be a score. You can call it as logits. It is called as logits. What are logits? Logits are simply numbers which are ranging from minus infinity to infinity. These numbers will represent something for each class. So this y cap, it will be a vector of k entries. Each of those k entries can be any number from minus infinity to infinity. These are called as logits. So it is going to output some scores. This is how you can see it. Okay. So you don't have probabilities here. Don't confuse this y cap with the kind of values y is taking. In y it is a one-hot vector. It is the true label. Whatever is the true label, in order to show that it will be a one-hot vector. Y cap, it will simply be real numbers which are forming a vector. Okay. So the next thing that you're coming up to is, given this real number, there should be some way of converting it into probabilities. So this is kind of raw model output, the y cap. We don't want that raw output. We want that converted into probabilities of different class. How can you convert it into probability? That is where softmax comes in. Softmax. Using softmax, you are going to convert this y cap into probability. How can you do that? Let us say I'll call that probability of, for each class you have to derive probability. Okay. For each class, y cap will have a value. Depending on this complete y cap vector, you want to find out probability of each class occurring. Then you can say whichever is having the largest probability, that is the class selected by your model. Okay. In order to find that, let us say you're finding probability of class k. That can be written as pk cap is equal to, see, in my notations, wherever I am using cap, that shows it is related to the actual output that is produced by the model. Okay, that is where I am using cap. So I want you to understand the differences. When I say y, it is the true label. But when I say y cap, that is what is produced by the model, not the true label. Similarly, when I say pk cap, I could have simply written pk for probability. I wrote the cap so that you understand it is derived from what is model output. Okay, that is why I am putting a cap. This can be softmax function. So it will be like this: e raised to yk cap, whichever yk is are you corresponding to. That is, for each class you have to separately derive this. Okay, e raised to yk cap divided by sum of all these. So sigma I is equal to 1 to k, or let us say, because it is class, I'll write k itself, or I, anything is good. I is equal to 1 to k. Then e raised to yi cap. This is what you call as softmax. What is the speciality of this? This softmax has a speciality. First I'll write the specialities. Then you try if you can automatically understand how those specialities are coming from this formula. Okay. The first one is, I'm saying sum of all probabilities. Sigma k is equal to 1 to k pk cap. That is the probabilities that you derive for each of the classes. If you sum all those, you will get 1. This is my first claim. My second claim is pk cap, this value always belongs to the interval from 0 to 1. These are the two claims. So let us see how these claims are kept here. First is this, second is this. First claim is kept because my denominator, this is the sum of all the upcoming numerators. That is e raised to yk. For each of these classes, I will be taking probabilities. If you sum all those numerators, that is what I am putting in denominators. which means if I sum all the values of pk cap, I will anyway get 1. So the first part is clear. The second point says it is always a probability which is 0 in between 0 and 1. That is because my new denominator is sum of all and numerator is 1 among those, which means it is a value between 0 and 1. Worst case, numerator can be 0. Best case, numerator can be same as denominator. Then it will be 1. My total probability will be 1. That is why both these claims are met. What does it mean when I say these two conditions are met? That means it can be interpreted as probabilities. That is you can see it like model is outputting a probability distribution because it is summing to 1 and each value is between 0 and 1. This is the logic. So this is why I explained all these things so that I can tell you, I can show you mathematically the output of the model. This can be interpreted as a probability distribution. Okay. Now let us get into how are you going to use this probability distribution and find out categorical cross entropy loss. Okay. Let us get into categorical cross entropy. See, I'm going it step by step and slowly so that you understand each of the parts clearly. We can actually run through this very fast, but I want you to understand each of the parts clearly so that you get the concept clearly in your mind. Once you complete this lecture, after that, the concept of categorical cross entropy should be crystal clear in your mind. Okay. Let us get into the next part. Next step is finding out the loss function. What I'll do is, first I'll simply write the loss function. Then we'll look into how it is coming, what it is, what is the logic. In case of binary cross entropy, maybe few lectures back when we learned about binary cross entropy, how did you write the loss function? If you remember, it was something like this: minus y into log y cap minus, or you can put this minus outside, then this will be plus 1 minus y into log 1 minus y cap. This is how we found out the loss function for binary cross entropy. So in case of categorical cross entropy, we are going to use the same logic and we are simply going to extend this into k different classes. So in case of categorical cross entropy, the same logic when extended to k classes, what happens? This will be minus of sigma k is equal to 1 to k, and what will be it? Yk into log of pk cap. This is what it will become. So if you see, this formula is actually also the same. That is, this is minus of sigma k is equal to 1 to 2 because only two values are here. One is corresponding to this y and 2 is corresponding to 1 minus y. So here whatever you said for two classes, same thing I just extended to k classes. That is when I'm calling it multinomial. Here if you see, y and 1 minus y, these are the classes. The same thing here I am depicting as yk. And here if you see, these are the probabilities. I told you the y cap is the probability of class 1 and 1 minus y cap is the probability of class 0. Same way, pk cap we had seen here is the probability of class k according to the model. So the same logic is used here, just that I converted it into a case where I can see it as categorical. Okay. Again, if the value of y you see, it can only take 1 or 0, because if y is the class, then this will be 1. If other class is the 1, then 1 minus 1 y will be 1. The other one will be 0. So among y and 1 minus y, 1 will take the value 1, 1 will take the value 0. Here if you see, my y was a one hot vector. Here I had showed you that this is a one hot vector. Because it is a one hot vector, or among all the yks, there will be one particular yk which will take value 1 and all other yks will take value 0. So this is the point that you have to understand. So effectively, what will be your loss function? If you do the whole calculation, this will actually be something like minus log py, something like this. I'll put a cap as well showing it as output. Something like this is actually this. That is, even though I'm writing it as sum of all, when you actually take the sum, what happens is among k classes, only one class will have value of yk equal to 1. All other classes will have value of yk equal to 0 because it is a one-hot vector. So when you actually solve it, because all other yks are 0, only one particular yk will take value 1, which is the model predicted true model, whichever is the true model. And your final formula will look like this, okay? Actually, only one particular log py cap term will remain. All others will cancel out because yks will be zeros, okay? I'll erase this again because I want you to understand that only one will remain. Formula is the above one only, okay? Now we know what is the formula. Next step is we want to understand how this formula came up. We have to understand. I simply wrote this formula now and I justified to you that this is the logic. Only one particular class remains. So log py cap is the formula used. But I have to show you how this is derived, how exactly this formula came. That is what we are stepping on to. Before that, I'll just explain you how this is logically right. If some particular value, some probability is here, if you take log of that probability, then it will be mapped to a value between minus infinity to 0. That when you take negative of it, it will take positive values, right? And whenever your probability is high, that is this value pk cap will be between 0 and 1. It will be a value between 0 and 1. Let us say for this particular yk, that is the right yk. I'm talking only about the actual true class here because I already told you final formula will only have one particular log remaining. That is only one particular py. Only this will be remaining. All others yk will be 0. Let us say for the true class, if the probability outputted by the model is something very close to 1, let us say 0.9 or something, my loss should be low in this case because the model is predicting the true label. When it is saying 0.9, it is almost close to 1 for the true label. So the loss should be lesser. Let us see what happens if you take log. If you take log of this value, I said 0 to 1, log will be between minus infinity to 0. Which means for this, the value of log will be something close to 0. When the value of log is something close to 0, that means my loss is lesser. And the next logic is when this probability is something close to 0, that is instead of 0.9, if probability is let us say 0.1 for the true class. This is actually wrong prediction. Then what happens? When it is 0.1, prediction is actually wrong. When you map here, 0.1 is very close to 0, which means if you take log of it, it will be very close to negative infinity. When I take negative, that is this minus sign is there. If you take minus of that value, it will be a very large positive value. A very large positive value will be your value of loss, which means here you made a wrong prediction, because of which your loss will be very high. So logically, this is right. This is the right way to depict loss. That is what I wanted to show. Now let us get into actual derivation of this. How did you actually reach this formula? You can't simply write a formula somewhere. There should be a mathematical base to it. Let us understand that mathematical base now. Okay. Keep in mind, finally we'll be reaching here. Okay. Whatever calculations we'll do, finally that is where we'll be reaching. I'm erasing of BCE formula. I'll simply write loss of y p cap is equal to minus sigma. I'm just rewriting this, okay? Copying. K is equal to 1 to k. K is equal to 1 to k. Yk into log of pk cap. So finally, I'll be reaching here. Keep this in mind and understand the whole derivation, okay? Let us start with this. We'll take the probabilistic, or you can say likelihood view, and from there we'll explain how it is reaching here. Let us see how this CCE, the categorical cross entropy, how this is originating from maximum likelihood estimate. We previously discussed in the maximum likelihood estimate lecture on how important a concept this is. So we are going to use that concept in order to derive categorical cross entropy. Okay. The first point I have to make is, what is our goal? If we are clear about this, then only we can be understanding everything. So what is our goal? What are we up to? What we want to do is, we have a model. For this particular model, we want to learn model parameter theta. Theta is the model parameter. What should be the speciality of this theta? This theta should be maximizing the chances that you see the training data. That is, you have a training data x, y, where x is the input and y is the output one hot vector. Then your theta, the model parameters, should be such that it will maximize the chances of seeing this data. It should give maximum chances of seeing this data. That can be written mathematically as probability of y given x theta should be as high as probable. That is, what should be this? It is model's predicted probability of correct class. That is, this means y is the correct class. What is that condition which will make the chances of the correct class being high? That is, given input x and the model parameter theta, you want such theta. Why am I saying you want such theta? Because your x is already fixed. Your y is also actually fixed, because you know what is the input, you know what is the actual output. Both these are already known. The training data already has your x, which is the input, and y, which is the expected true label, actual true label. Only thing that is variable here is theta, which is the model parameters. So you have to find out that particular value of theta, which will increase probability of y given x theta. That is, given theta and input x, the chances of seeing the true label y should be maximized. This is what we are going to do in maximum likelihood estimate. Okay. So this, another way of writing this is, okay, let me write this clearly. Instead of simply writing y, I'll write p of y is equal to k given x and theta. That is, y being the class k given the values x and theta. So this can be expressed as, so the goal is clear now. I'm erasing this off. We want to maximize p of y given x theta. So it can be written as p of y is equal to k given x and theta. This can be written as what? Pk cap. And this pk cap, this we already explained. What did we explain? We explained about this pk cap here. Here we have already explained about what is this particular value pk cap. So I am going to write it again here, or I don't need to copy, right? You already saw this here. You can see it from here. I'm not copying. So this value will be my pk cap. Okay. I want to maximize pk cap. Pk cap value should be maximum. When I have the output from model, among each of the k classes, whichever is the kth class which is belonging to the true label, that class probability has to be maximum. This is what I want to try. I want to find value theta that will do this. Okay. The next step is, these particular values are clear for you, right? Your yk, you can see it as the logit or the raw score for kth class. Your theta, okay, I'll write here theta is your model parameter. Okay. Model parameters is what you're calling as theta. And then what is this pk you already know. It is the probability of kth class. Let us say you have some data set. Okay. I'll write the data set as this. xi, yi is each pair. So you have xi, yi. Similarly, you have, let us say, n different data, training data that is given. You have n different data. How will you write? I is equal to 1 to n. That means you have n data samples which are having values xi and yi. Okay. What do you want to do? The likelihood of observing all the true labels under this model should be maximized. How can you write the likelihood? So here you have xi and yi, where yi is the true label. N examples are there. What do you want to do? You want to maximize the likelihood of observing true label in all these n cases. How can you do that? Likelihood can be written as L theta. So L, you should understand, it is likelihood. Okay. Pi of, that is product, I is equal to 1 to n. In each case, what is it? Probability. This probability can be P of yi given x theta. So what do you want to do? You want to find out maximum likelihood. And what is your likelihood? Likelihood is the product of each of the probabilities. That is, here I am taking n different classes, n different examples. For each of the examples, this is the probability that it belongs to the right class. What do I want to do? I want to maximize the probability of all the classes hitting the right, all the examples hitting the right class. So for all the examples, the probability of right class should be maximized. That is what I am writing as product of all the probabilities of right classes be maximized. Okay. Next thing. Now I know what is my likelihood. Next thing is, you want to find what is to be maximized. What is to be maximized? This likelihood is to be maximized by finding such value of theta that will maximize. How can you write it? That value of theta I'll write as theta cap. What is this theta cap? It is argmax, that is whichever value maximizes, whichever value of theta. Argmax theta means whichever value of theta maximizes L theta. That is what I'll call as argmax theta. That is theta cap, which is my maximum likelihood estimate. Okay. What did we learn in our previous maximum likelihood estimate classes? Whenever you want to find out maximum likelihood estimate, you should always play in logs and do not play in the actual likelihood. Why is it? Because it increases your numerical stability. What I'll do is I'll cut this out and write here theta cap equal to argmax of theta L theta. What I'll do is here, instead of L theta likelihood, we'll take log likelihood. So if you take log likelihood, it will be log L theta. What happens here? Product will turn to sum, right? Then it will be sigma I is equal to 1 to n log of this probability. So it will be log of P of yi given xi theta. So this is your log likelihood. What is the next step? If you remember whatever we did in case of binary cross entropy, the same steps we are following here. So I want you to clearly understand the way we are following those steps and converting those to multi-class case. Okay. So after we find out the log likelihood, we already discussed that whenever you want to maximize log likelihood, the better version is to take negative of log likelihood and minimize it. See, both are the same. You maximize a value. Instead of that, you minimize negative of that. It is one and the same. So what can you do? You take negative log likelihood and then you try to minimize. That is an easier way. So, and moreover, it is because it is a loss. So you should always minimize loss. You should not maximize loss. Then what is the point? That is, if I'm saying that in order to make my model perfect, I want to maximize loss, that doesn't make sense because loss should always be minimized. That is when my model should perform at its best. What I'll do, I'll take negative log likelihood. How can I write negative log likelihood? Negative log likelihood. So this is just negative of this value. This is log likelihood. If I simply put a negative sign, it will become negative log likelihood. So minus of sigma I is equal to 1 to n log of yi, okay, log probability of p of yi given xi theta. So I just copied whatever is here and I put a negative sign in front. Okay. So this is your negative log likelihood. What else do you want to find in order to solve this? One more thing that you want to know now is, you know all the parts except one part that we haven't clarified properly. Which is that one part? That one part is, what is this value probability of yi given xi theta? What is this particular value? So this value I have told you here. Here I have told you it is your pk cap, that is whichever is the probability for that particular class, right? But the problem here is, you don't know which is the probability of true class. You have probabilities of all the classes. Mathematically, you want some way of expressing it such that this will show just the probability of true class. That is, you have probability of each class, that is p1 cap, p2 cap up to pk cap. All these probabilities you are having because you computed here. Here you computed all those. So you have the probability of each class with you. But what do you want? There will be one particular class k which is the true class. So this kth class is where the true label belongs to. For this particular input, true class is kth class. For that kth class, let us say it is second class is true, then you only want this value p2 cap, whichever is the true class, corresponding to that class, whichever is the probability, that should be substituted here. What is the mathematical way of expressing this? Just think about it for 10 seconds, then I'll tell you. Think about for 10 seconds, what is the mathematical way of expressing it such that the true class probability, that should be substituted here. Whichever is the true class among these, that particular class corresponding probability that is found by the model should be substituted here. What is the method? This is the way. So this probability can be written as, that is p of yi given xi theta. This can be written as, the way of writing it, this is given. This can be written as product of k is equal to 1 to k pik cap raised to yik. What does this mean? Just think about this mathematically. What does this mean? This means you have k classes. Okay. We are talking about ith example. So I is equal to 1 to n. You have n example. I already told you. Let us take case of one particular ith example. For that ith example, you have already found out k different probabilities, which are the k different probabilities that the model is outputting. Out of those, you have to find that particular probability which is corresponding to true class. So you are using the one hot vector y which is corresponding to that particular example I. For the ith example, one hot vector will look like something like this, maybe 0, 0, 0, 0, 1, 0, 0, something like this. So wherever you have yik equal to 1, that is the true class. Now think back with this formula, what happens? It will be like this. When you expand, this will be like p1 cap raised to y1, p2 cap raised to y2, p3 cap raised to y3, so on up to pk cap raised to yk. So among all these y's, everyone will be 0 except one particular y which is the true class. So when y is 0, automatically this whole thing will be 1. p2 raised to y2, this whole thing will become 1. But whichever is having the right y3, that is among the one hot vector, whichever is having value 1, for that p3 will remain. Let us say 3 is the right class here. Then p3 will remain, all others will become 1. So when you multiply p3 with all ones, it will be p3 that remains. So this is the mathematical way of expressing that the right class corresponding probability should be kept. Okay. So at this point, you are keeping pik cap, which is corresponding to the right class. Okay, understood this logic here? Let us move on to the next point. So now that you got this point, next thing is, to the log likelihood I am going to substitute. So here I want negative log likelihood. So I am going to take the first part, that is log probability of this. If I take that part, it can be written as, how can it be written as? Probability is this, then log of probability, log p of yi given xi theta. This can be written as, what is the way of writing this? When I am taking log of this, what happens? Product will be turning to sum. So just think like this. I am taking log of pi k is equal to 1 to k pik cap raised to yik. When I take log, this product will turn to sum. So I can write as sigma k is equal to 1 to k log of this value. What is log of pik cap raised to yik? This can be written as yik will come in front. It will become yik into log of pik cap. So this is the way of writing. So now you found out the log of probabilities. In negative log likelihood, what is your actual term? It is having a negative sign in front, and you have to consider all the n samples. One thing keep in mind, this one I derived just for the ith sample. You are having I is equal to 1 to n. I told you, you have I is equal to 1 to n. N different samples are there. Here we considered just one sample. Here we were considering all the n samples. That is why there is a sigma I is equal to 1 to n in front. But here I just considered one sample so that explanation becomes easy. Here also we considered only one sample, only the ith sample. But actually we have to sum over all the n samples like we did here. So now your negative log likelihood, which can be written as loss, your negative log likelihood. So whatever we wrote here, negative log likelihood, it can be rewritten as minus sigma I is equal to 1 to n. So keep an eye here. Whatever is here, I'm just copying, but each of the term I'm writing the right terms in front. Okay, instead. So I equal to 1 to n will stay as it is. But for the remaining part, log p of yi given xi, for that part I'm going to substitute this thing. Okay, this is the substitution I'm going to make for the log part here. What I'm going to write? Sigma k is equal to 1 to k yik log of pik cap. This is the right way of expressing. So negative log likelihood is what you want to minimize. This is the term that you have to minimize. So what do you have to minimize? Negative log likelihood, which is your loss. So instead of negative log likelihood, I am going to write as loss. So this is your categorical cross entropy loss. What you actually want to minimize, that is what you are going to call as loss. Now let us compare whatever we found out here, this thing, with whatever we initially wrote as categorical cross entropy formula. So if we see that formula, here we wrote it. Now if you compare, what you will understand is, here you had only k classes. You did not consider I equal to 1 to n. That is n different examples we did not consider, which we should ideally consider, because you will be having n different training samples. You won't be having a single piece of data and training on one data point. Instead, you will be having n different data points and you want to find loss of all those. Okay. So here I wrote it only for one sample out of these, and in my final answer I am considering all n samples. That is why there is one additional summation term, otherwise that won't be there. So actually you should have this term because you are considering n samples. Okay. The remaining term is k equal to 1 to k yik log pik cap. So if you can compare this here, it is the same term, just that the I is not considered. Yk log pk cap. So I derived this formula by using maximum likelihood estimate. This is the logic you should know. So we'll just walk through this and then we'll complete this lecture with a basic explanation. So categorical cross entropy, we considered k as number of classes. We had true labels which are actually represented as a one hot vector y. Then you have x, which is the input. Y cap is the raw model output. Okay, that is logits. Logits are converted to probability using softmax. These two conditions are satisfied, which means it can be considered as probabilities. So your model is outputting a probability distribution. Okay, after softmax. That is after softmax. Then we told that this is the loss function minus sigma k equal to 1 to k yk into log pk cap. Though we want to find out the right values of theta, maximum likelihood estimate. For that, what should be the loss function? Whichever maximizes the chance of this probability, the kth class, whichever is the class belonging to right label, the probability of that should be maximized. That is the aim. Then we said we have n different inputs which are having xi as the input and yi as the output. Then your likelihood can be written as product of all the probabilities. For each of the n inputs, the probability of right class, that should be maximized. This is what you want to do. If you want to maximize likelihood, we discussed this is the aim, maximize likelihood. Instead, you can maximize log of this term. So you took log likelihood, log L theta. That is what this formula is. From there we said, instead of maximizing log likelihood, a better option is to minimize negative of log likelihood. So we went on to take negative of log likelihood. Then we tried to find out each of the terms there. This probability term that we defined can be written as this, which would just highlight that particular probability which is of the true class, right? After that, what did we did? We found out log of that, log of probability, that is log likelihood. Then this negative log likelihood, we were able to write it as this formula. So this is your negative log likelihood, which can also be called as categorical cross entropy loss. So this is LCCE, categorical cross entropy loss. What do you understand from here? You understand that high probability for the correct class. That is, for the correct class, if you are having very high probability, then your loss will take the least possible value. Whenever the probability of your correct class is low, whenever that is low, your loss function, it is going to take very high value. So your loss will be higher whenever prediction is wrong and loss will be lower whenever prediction is right. So this is the logic. Another way of stating this could be something like this. You can say negative log likelihood of the correct class under softmax model. This is what you call as categorical cross entropy loss. Okay. So the next thing we have to do is we have to actually find gradient of loss. Whenever you know about a loss function, you should be finding gradient of that loss function, because for gradient descent and all, you will require gradient. You should know how you can find out the gradient of a loss function. What we'll do is, because this is your loss function and gradient is not very straightforward, I'm not saying it is very difficult, but it takes some time to derive the gradient. So we'll take it up in a different lecture. Next lecture, we'll find out gradient of categorical cross entropy loss. So for now, we have found out how this categorical cross entropy loss is coming up. In the next lecture, we'll see how to find out gradient of categorical cross entropy loss. Okay.